Assalamualaikum and salam sejahtera. My name is Badrul Hisyam. My presentation will be on the design of low molecular weight pectin and its nanoparticles through combination treatment of pectin by microwave and inorganic salts. This study examines primarily the molecular weight and degree of esterification profiles of pectin in response to treatment by microwave in combination with monovalent and divalent inorganic salts. Then, the possibility of formation and physical attributes of nanoparticles prepared from this modified pectin were assessed against their suitability for use as nanocarrier in cancer therapy. So, in this study, we propose microwave heating treatments to modify pectin to lower the molecular weight and size. The microwave technology offers lower activation energies, higher reaction rates, reduced reaction times, fast temperature increment, and finally is a chemical-free operations. From previous studies, polymer modification by microwave is commonly assisted by inorganic salts, either monovalent or divalent, which produce localized superheating action to the polymer. The objective of this study first is to modify the pectin by means of combination treatment using microwave and inorganic salts. Secondly, comparison was made between sodium chloride and calcium acetate for the localized superheating action towards pectin. And this is the methodology of the experiment. Pectin was first dissolved in distilled water to produce 2% pectin solution. Then, inorganic salts of sodium chloride and calcium acetate were introduced as initiator. And then the whole mixtures were microwaved at 900 watts at various times. It was suggested that the divalent nature of the soluble calcium will enable it to cross-link with anionic pectin side chains through the carboxylic functional groups, and hence pull the pectin closer as compared to the monovalent sodium ion. This will allow better heat transfer to the pectin and induce the degradation rate. Finally, the degraded modified pectin was nanosprayed to form nanoparticles to further decrease its size in order to be used as carrier in drug delivery system. The results showed that the specific viscosity of the pectin solution decreased when subjected to longer microwave irradiation, and apparently the use of sodium chloride in the process of microwave treatment was accompanied by a greater reduction in the specific viscosity of the pectin compared to the calcium acetate. And theoretically, the specific viscosity of a polymer solution is well known to be directly related with the molecular weight of the polymer. Here we can see that the molecular weight of the pectin was lower when it was subjected to longer microwave irradiation. And it is interesting to note that the molecular weight of pectin produced with the presence of calcium acetate was lower than compared to the sodium chloride. We also studied the molecular weight distribution of the modified pectin as quantified as polydispersity index. And from the figure C, we can see that the lower polydispersity index was obtained with prolonged treatment with microwave. So the reason why calcium-induced microwave modification of pectin resulted in higher specific viscosity compared to sodium-induced might probably be because of the formation of a pectin egg ball structure. Pectin crossing could induce chain aggregation and resulted in higher viscosity, although the molecular weight observed was smaller. And pectin egg ball structure also helps keep the chain closer together, and this will allow better heat transfer to the whole pectin molecule. Finally, these figures show the SEM images of nanoparticles made of untreated pectin and pectin treated with microwave and inorganic salts. The nanoparticles were spherical in shape, and nanospray drying of pectin tend to result in the formation of nanoparticles that have smaller physical size than the pectin itself. In conjunction with the present experiment, the pectin treated by combination of microwave and inorganic salts was concluded to be beneficial to be used in nanoparticulate drug delivery system for the treatment of cancer. Their nanogeometry was smaller than the pore cutoff size of tumor vasculature, which is around 400 to 600 nanometer. In conclusion, combination of microwave with calcium acetate brought about the formation of pectin with lower molecular weight and degree of esterification, but higher solution viscosity than that of with sodium chloride. The formed nanoparticles from pectin treated by microwave in the presence of inorganic salts had a mean size smaller than 600 nanometer. They were deemed suitable for use to encapsulate cancer therapeutics with respect to permeation and retention attributes of tumor vasculature. On that note, I conclude my presentation. Thank you very much for your attention. Assalamualaikum.